page 7, here we have a special case, right? When we play pool, right, billiards, the masses of each ball or cue ball and the target balls are all pretty much equal masses, okay? If you were to strike a cue ball with a cue stick and then let the cue ball hit a target ball that's at rest, all right? So it's important to understand that this target ball is at rest. And they're equal masses. And they also tell you that it is an elastic collision. That means elastic collision tells you automatically that sum of all kinetic energy initial must equal to the sum of all kinetic energy final after the collision. Okay? So here is the initial condition before the collision, and here's the final condition after the collision. Okay? So if we were to look at the initial total momentum, I only have mass of the cue ball. Whoops. The cue ball is the only one that is moving. Okay. So total initial momentum is just the cue ball's momentum. Okay. After it hits the target ball, right, this will go off at an angle, and the mass of the target ball will go off at an angle. Okay? So if we were to look at the conservation of momentum for before and after the collision, right, these two added together should equal to exactly this. Okay? So if I were to redraw this out, no, it's not going to be exact, okay? So I'm going to just do my best to fake it to make it look exact, okay? Again, this one, if I were to draw that, here, this one, so this P2 final, right? And this is P1 final. So this is P1 final. And this is P2 final. Should add up to, this plus that should add up to this P initial. Okay. So when we add these vectors the resultant vector should be basically the initial momentum vector. Okay, so we definitely have a triangle here. But what is this angle here? Well, let's find out. Okay, so this happens for all collisions, by the way, right? So we'll talk about that. So all collision says, right, the total initial momentum is equal to total final momentum, right? So if we were to look at now, because it is elastic collision, and because elastic collision, this must happen. So let's take a look at what happens when we look at the kinetic energy part. So sum of all kinetic energy initial must equal to sum of all kinetic energy final. Initially, I should only have 1/2 m1 v1 initial squared. That has to equal to, right? I should have 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. However, m1 and m2 are equal to each other, right? So m1 is equal to m2, which is equal to m. That means I can literally cancel 1/2 m's out. That means my v1 initial squared is equal to, right, v1 final squared plus v2 final squared. Does that look familiar? This looks like a Pythagorean theorem. So if I were to draw v1 initial, v2 final, and then v1 final, this only works for right triangles, right? So if I were to draw out, here's my v1, here's my v1 initial, and then here's my v2 final, and here's my v1 final. That means this angle must be right angle. Okay? So this only happens if and only if, right? V1, V2 final, and V1 final are perpendicular, okay? This is Pythagorean theorem, basically. Okay? So if you don't put any spin on the ball, like if you don't put any English on the cue ball, then if you hit the cue ball directly at the center all the time, when you hit the other billiard ball, they should go off at 90 degrees. Okay? But if you actually hit the cue ball at a different spots, right, then it will go off at different angles other than 90 degrees. So if this were the cue ball, if you were to hit it directly at the center, right, with a cue stick, and this will happen 90 degrees. But if you put any kind of English on it, like here or back here, this will give you backspin, right? This will follow the ball after you hit it, and so it's all this different English on the cue ball would put different angles out. But as long as you're hitting directly at the center, you will go off at 90 degrees. All right. So something good to know. All right. Next. So let's think about what would happen if we have elastic collision happening again in one dimension. So instead of going off in two dimensions, let's say it's confined to stay in one dimension. Okay, so one dimension collision, no scattering. Okay, it's a head-on collision, right? So right, head-on collision, right? No scattering, okay? So it's going to be confined to one dimension. Okay? So that's one parameter. Second parameter, it is elastic collision. Okay, that means the kinetic energy is going to be conserved. Right? The third parameter that it has to have is the target ball must be at rest. Okay, so if we have this, M1 coming in and it collides with M2 that's at rest, and they're equal masses, right? So what happens? Okay. So all these conditions must be there before we even start. Okay, so it's very important that all these conditions must be true. Okay. So calculating the V1 final. So after the collision, so this is before the collision, obviously. What happens after they collide? Okay. So we're looking for V1 final. And what happens to V2 final? Well, we'll have to figure that out as well. All right. So let's take a look at conservation of momentum first. We know the momentum has to be conserved no matter what collision it is. It's always conserved. So initial momentum is just m1 v1 initial, because this is the only one that's moving and target balls at rest. After the collision, we're going to have m1 v1 final plus m2 v2 final. Now we don't know which way they go, or we don't even know what's going to happen to this. Okay, but we do know these two momentum have to add up to whatever the initial momentum we had before the collision. All right. If I bring this m1 v1 final to the other side, and it becomes negative, and factor out the m, I would have this. Then, if I were to bring this m2 over to the other side and square both sides, this is what I would end up with. So here is my equation 1. Okay. This came from conservation of momentum. Now, because it is elastic, right? Because it's elastic collision, this must also hold true. Not only momentum is conserved, but the kinetic energy is also conserved. Okay. So here, 1/2 m1 v1 initial squared must equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. I can cancel out the 1/2s. Okay. And by bringing this m1 v1 final to the other side and factoring out the m1, this is what I would get. Okay. Then if I divide both sides, this is messed up, sorry. This is typo. This should be V. All right. If I divide both sides by m2 and factor this out, this is what I would get. So this is equation 2. And so this should be V2 final squared, okay? So this one's okay. Now, if you were to look at V2 final squared, V2 final squared, so if I set them equal to each other, right, then I would get, right, so let's set 1 equal to 2. Then what would I get? Well, let's take a look. I would get, right, m1 squared over m2 squared times v1 initial minus v1 final squared must equal to m1 over m2 times v1 initial plus v1 final times v1 initial minus v1 final. Now, as you can see, I can cancel out this with this and this with that, right? And if you can cancel out one of these with one of this. Now, if I distribute this through, I would have m1 over m2 v1 initial minus m1 over m2 V1 final, right, must equal to V1 initial plus V1 final. Okay? All right. Now we're going to try to isolate V1 final. Okay? So since we have V1 final here, right? And then we have V1 initial here. Let's bring all the V1 finals to the other side and V1 initial to the other side. So here I would have M1 over M2 V1 initial, right, minus V1 initial is equal to, right, I would have V1 final plus M1 over M2 V1 final. Now, since these coefficients have M2 in the bottom, let's make these legit by multiplying M2 over M2. I'm not really changing it, I'm just multiplying it by 1, right? Same with this, M2 over M2. Okay? Then, I could pretty much cancel out all the bottom M2s, right? Factor them out and then just divide it out, right, basically. So all I have is this on this side, which is I can factor out the V1 initial, right? So V1 initial is M1 minus M2 is equal to, here again, if I factor out the V1 final, I get V1 final, and I get M2 plus M1. Right? Therefore, my V1 final, if I solve for my V1 final now, is equal to, right, M1 minus M2, right, divide that by, right, M1 plus M2 times V1 initial. So now that we solved this and derived it together, you don't have to keep deriving it to use this equation. You can use this equation without deriving it now. So use this. Well, what's the significance of this now? What happens when M1 is equal to M2? So what is V1F, right, if M1 is equal to M2? Come on, somebody answer.
It'll just be 0.
Yes, it'll be 0, right? V1 final will be 0. That means it's going to come to a stop after the collision. Okay? It will come to a stop after the collision. All right. So, is it true? I wish I had demonstration, materials with me, but I don't. So, next time I'm at school, I can show you. But this is close enough to show you a demonstration where I have two identical masses. One is going to be at rest, other one comes in. And according to this equation, if this comes in and crashes into the other one, this should stop, right? This should stop after the collision, and the other one is going to take over its momentum, right? So since we did it this way, I think maybe we should do it this way. So here we go. Ready? Well, it does stop, right? It does stop. So this equation holds, okay? So one stick comes in, the initial velocity, right, of the M1 comes in, so final velocity of this initial M1 is going to be 0. All right? All right, that's going to drive me nuts. All right, so hopefully that's close enough demonstration that this equation does hold. All right. Righty then, let's take a look at second part of that. What if they're not equal masses, right? What if they're not equal masses? Then what? Okay. By looking at this equation here, okay, the one we derived together, okay, and if we were to solve for V2 final, this would be the other equation, okay? So, again, I'm not going to waste time and derive this again, but you could derive this on your own, okay? So these two equations you should be able to use. It's the same concept how we derive this, but instead of V1 final, we just do V2 final and solve for V2 final instead. Okay, so make sure you see that this is something that we can use, and this is also something that we can use now without deriving it. Okay. All right. So let's take a look at what's going on. Okay. So V1 initial. Okay. If the mass of M1 is less than mass of M2, when this comes in, all right, here my M2 is bigger than my M1, so my final velocity of my M1 is going to be negative, right? So M1 minus M2 is negative, right? Right? Therefore, my V1 final will be negative. It means it will go backwards, right? Okay. However, here, this will always stays positive. V1 initial is positive, so my V2 final will always be positive. So that was easy, right? So my V2 final okay. Maybe I should have like boxed this in green instead. Okay. Make this one green. Make this one green. Make this one blue. Right, and make this one blue. Now what if M1 was bigger than M2? Right? If M1 was bigger than M2, what's going to happen? In this case, m1 minus m2, if m1 is bigger than m2, it will be positive, right? It'd be positive. Therefore, my v1 final will be positive. That means m1 will go forward, right? Okay. What about, well, this will always be positive, I guess, then, right? This will never be negative. So v2 final will be positive. Right? So, what happens? Well, if you collide, like let's say you're driving a smart car for two and collide into a Suburban, right? Smart car for two will bounce backwards. When you bounce, you're going to get the greatest change in momentum, which means you will have the bigger impulse. So you're going to get more damage to you and to your car. However, when Suburban crashes into a smart car for two, Suburban won't even feel it, right? There won't be hardly any change in momentum. It'll just continue to plow through, and the smart car for two will shoot out and basically hit a car in front of you, right? So the moral of the story is drive a big car, you know? All right. So when M1 is bigger than M2, right, then this what happens. Now, what happens when M1 is equal to M2? This is messed up. When it's equal to M2. We already saw what happened, right? We knew what happened. I already showed you a demonstration that M1 is going to stop, right? So V1 final goes to 0, right? Because M1 minus M2 is equal to 0, right? So what happens then? Well, then if we look at here, M1 and M2 are equal to each other, then this would be 2M, and this would be 2M. So this would be just 1 if M1 is equal to M2. In that case, your V2 final will be same as your V1 initial. Okay? Because 2m over m plus m V1 initial is your V2 final. Therefore, V1 initial. This will become just 1. All right? So, this can be easily demonstrated with Newton's cradle. Right? Newton's cradle is what we just saw earlier. Okay. So if we were to look at our Newton's cradle, if one ball comes in, right, and strikes the other one, right, somehow it knows, this thing is magical actually, it knows that only one ball came in, and instantaneously this will come in, stop after a collision, which means this will start moving with this velocity and collide with this instantaneously, that means this will stop and this will take over. And then this will come in and this will stop and this will take over. And this will take over the other one and this will stop. And then there should be only one going out. And boom, there it is. Right? So that's no real magic, right? So what happens? Instead of just one coming in, what if we had two coming in? Right? What would happen instead of one coming in to crash into it? We have two coming in. Well, if we have two coming in, then it's going to be like acting like 2m coming in rather than just one, like big. Well, you could think of it as one big giant 2m actually, right? So how's this going to behave if two are coming in for the first one right there, right? This one right here. What would the outcome be, right? Let's make a prediction, right? How many would say, by show of hands, how many would say one's going to come up twice the speed on the other side? No hands? Okay. How many would say two's going to come out at the same speed that, these two initial came in? All right. Good. 9, 10, 11, 12. All right. I think the second one has it. All right. I'm glad 12 people are at least paying attention. Thank you. All right. So let's see what happens if I have two coming in and somehow magically this thing knows that only two came in. All right. So maybe we can draw that out. Okay. Maybe we can draw that out and see what that looks like. All right. So when two came in, okay, two went out. Right. So here I can say, okay, 1, 2, 3. So it's like 1, 2, 3. And then 4 and 5 went out. Okay? So if you want to, you can draw that. All right? What about when these two come from the other side? Make a prediction, and see what's going to be like when that happens. All right? So here I have 1 and 5 is crashing in. All right? 1 and 5 is crashing in. And let's see what happens. All right, here we go. So, stoy. Nothing magical, right? So it looks like they're going back out. Exact same speed they came in, okay? Now, obviously, it's going to eventually lose energy because it's got the sound and heat generated, but, and this is not perfect either. If you can see, there's a gap between these two balls. They're not touching, and there's a slight gap here, too. So if I were to, so it's really not perfect. They should be all touching, but they're not. All right, so all right, so it's actually pretty cool that they behave the same way. Okay, so here for this one, okay, so we're going to have 2, 3, 4, and then we're going to have 1 and 5 going the other way, right? So 1 and 5 goes back out. And I got 2, 3, 4 remaining at rest. All right. So when we did 2, right, we got 2 going in, 2 going out, right? So what if we do 3? Now we don't have third ball on the other side, right? We don't have third ball on the other side. So what's going to happen? Well, the middle ball is going to be like a switch hitter, right? It's going to actually compensate to the other sides that's needed, okay? So, okay, what if we do 4? Right? There you go, right? The 3 in the middle will compensate. What if we do 5? Okay. All right, fine. All right, so as you can see, it would actually compensate the other way, right? Now, if we had something really different, like the next one, 2 and 5, like 1, 2 coming from one side, 5 coming from the other, right? And then we get it switches, right? So right, it switches. So this will take over the other side, and these two will take over this other side, and so on, right? So here we have 1 going this way, right? And then we have 2, 3 staying, and then 4, 5 going this way, right? Wow, wow. Then what about the last one? Right? So if we had 1 coming in from left, 3 coming in from the right, right? So let's see. Stoy. I said stoy. Here we go. Yeah, so still behaves the same way, right? So 1 comes in this way, 3 will go out the other way, right? So we have 3 would go out. So 1, 2, and 3. 4 would remain, and 5 would go out this way, and then this way. Okay? So you could see that momentum will always be conserved. I wish it was a little bit better. Okay? All right. This thing's been played around in class so much that it broke. And my son had to fix it yesterday. Anyway, so hopefully that explains page 10. All right? I wish I could show you a demonstration of this in school. I don't have basketball and tennis ball here at home. Come on, I'm Asian. I don't play basketball, right? Anyway, if I were to drop a tennis ball and basketball where I place the tennis ball on top of the basketball, when this thing is dropped simultaneously together, matter of fact, the tennis ball and the basketball are attached, like by, just by contact, basically, okay? You can cheat by putting in a tiny bit of like a tape there so they stick together, right? When the basketball hits the ground and bounces back up, the tennis ball just shoots right up, a lot higher than where it started from. It's a mystery, you know? So, in a normal situation, I guess, if I drop a basketball, right, it's going to bounce back up, right? Not as high as where I dropped it from, right? Because it's going to lose some energy due to heat. And same thing, if I drop a tennis ball, it's not going to rise up as high, okay? So it may rise back up to maybe here, right, for the basketball. And for tennis ball, it may, you know, back up here, right? Depending on, I guess, how much of a collision it had, right? So it's not going to bounce up any higher than previously where I dropped from, okay? But wow, how does this happen? You know, I mean, it's more dramatic if you actually see the demonstration, right? But I'll show you when I get back to school, okay? So here's what happens. It's like relativistic velocity, okay? When the basketball bounces off the floor, and let's just say in an ideal condition, it doesn't lose any energy at all and bounces back up exact same velocity that it hits the floor, all right? There's no kinetic energy lost. Let's just pretend it that way so it'll be easier to understand, all right? That velocity going back up for the basketball is same as basically the tennis ball coming down to meet the basketball, and at subatomic level they're not, like, you know, they're not touching, right? So when this thing changes relative motion to the tennis ball, right, as seen by the basketball, this thing is coming, right, twice the v. Because if you are standing here, or like let's say standing here, and you're watching the tennis ball come down, right? Because the basketball is going up at v, right? This tennis ball is going to look like it's coming at 2v, right? Relative to the basketball. Okay? So, relative to the basketball observer, this is going to look like it's coming down at twice the speed. All right? Now, the motion of the tennis ball with respect to the ground then, after the collision, will be shooting up at twice the v, right? Because now, because of its bounce, this thing's going to move off at twice the v. However, because now the basketball is bouncing up with v, this will be pushed with another v, giving it a 3v. Okay, so this is the, you know, this is the tough one right here. So here this will be 2v, right? We normally expect, right? But now we also get, right, this v right here from the basketball. since the basketball, right, is a moving platform. Okay? So, relative to the ground, so if we were to observe from the ground, right? If we were to observe from the ground that this thing is going, right? The tennis ball is going to be moving 3 times v. Okay? So therefore, 1 half m times 3v squared is equal to mgh, so kinetic energy, potential energy, remember? What we get is, right, well, I guess the masses can't cancel out, right? We would get 9v squared, right? 1 half 9v squared is equal to gh. Normally, right, normally it would be just, 1 half mv squared, right, is equal to mgh, right? So when the masses cancel out, my h would be, right, v squared over 2g, right? But here we get 9 times, right, v squared over 2g. Therefore, the height will be 9 times the h. Okay? 9 times the h. So it would shoot up 9 times as high, right? So if we were to say no kinetic energy lost here, right, and then let's say it bounces back up to original height, right? This height that we gain, where compared to this height, the tennis ball is going to rise up 9 times the height that it would get if we did not lose any energy during the collision. Okay? I know it sounds kind of crazy, but it does. But it's not going to go 9 times as high because we're going to lose some energy, right? But it does go pretty friggin' high. And I could show you next time when we're at school. I don't know how we're going to do that, though. I got to get like a camera crew to like videotape this. Because if I do it in class, like it'll go through the ceiling. We'll work it out. All right? So, well, what if we then put something else on top of that? Like, I don't know, like a golf ball, So you have basketball, and then we have like a tennis ball, and then we have a golf ball. And then what if we like put like a marble on top of the golf ball, and then like a steel BB on there or something? Maybe you could shoot it to the moon, right? I don't know. Let's take a look. If just putting another golf ball up there, see what happens. Right? Here's a challenge question for you. Instead of golf ball, because that would be really, bad if it goes through the ceiling tiles. So we'll put ping pong ball, so it's not going to be as massive, right? We put ping pong ball on top of the tennis ball, on top of a basketball. how will the ping pong ball go, right? So from the last, right, from the last thing we did, right, if we were to look at, how much basketball will be going up, right? So since basketball is moving up, right, with V, right, we said um, tennis ball, right, will be going up with, right, 3V, right, because this is going up at V. And then we said this is 3V, right? So now the tennis ball becomes the moving platform. So I'm going to redraw this here. So tennis ball is going to be now the moving platform for the ping pong ball. So this is going to be 3V, where the ping pong ball is coming down at a V, right? So when it bounces, what's going to happen? When it bounces, this ping pong ball is going to shoot up with 4V now, right? 4V. So we have 3V, right? And then we have 4V. So this thing is going to be going up at 5V, right? So with respect to so if we were to have the observer from the ground, right, looking at this, you'll be getting, right, we get 7V. Okay, we get 7V. So because this is moving platform with 3V and this is going 4V, right? 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 So we have 3V plus 4V is now equal to 7V. Okay? Therefore, 1/2 m times 7V squared is equal to mgh, right? So now h is equal to 49 normal h. So it's going to go up 49 times higher. Now, if it's perfect, right? I mean, there's no energy lost and etc. In that case, it's going to go 49 times higher than the normal height, okay? Where it's dropped from. So we know it's not going to drop. When we drop from this small h, it's not going to go back up to small h. But if we make it perfect where it doesn't lose any energy, then yes, 49h. Right? But we do lose plenty of energy. It may not be exactly 49h in real life. All right? All right. All right. We're almost done, people, believe it or not. So let's talk about gravity assist slingshot, so you guys can work for NASA or maybe even Elon Musk and SpaceX. Right? Gravity assist slingshot is actually pretty cool, and it actually works. One of the first person to actually introduce this is Arthur C. Clarke. When we decide to send probes out into our solar system, they use gravity assist slingshot so that we can actually send these probes further out from our solar system without losing any energy. Matter of fact, it gains speed once we go through this. If you ever watched that movie Martian, right? They use gravity assist to slingshot that spaceship back to the Mars, right? Instead of turning the spaceship around, they actually use Earth gravity to slingshot it off to send them back to Mars again, right? So how does this work? It's very similar to like the collision of the tennis ball and the basketball. All right, relative motion basically was what it is. Okay, so here's the Earth observer, right? Okay, so let's say probe is coming in towards the planet, right? As the probe is coming in towards the planet, right? There's basically a gravitational collision happening. Okay, it gets sort of captured by the planet's gravitation, and it falls into the planet's gravitational orbit, basically. And then, as it comes to the other side, right, you're going to actually do a little burn here, right? So in order to get captured into this planetary orbital, I guess, path, you have to slow it down slightly so that it falls into that orbital path. And if you slow it down at the right speed and falls into the orbital path, and then it gets swung around at right here, you give it a little burn to escape that orbit, right? But the planet is not a stationary thing. It's actually moving, right? It's moving. So because the planet's moving and probe is coming in and swings around the other way, you're going to have that same V of the platform, that basketball platform, right? So if we were to observe this motion from Earth with a large telescope, right? I know we're moving too, but let's say we're stationary, okay, and observing this, right? What happens, right? So perfect bounce, right, will be basically we don't get anything lost, right? Nothing is really like lost. So think about this gravity capture as gravitational collision, okay? Right? So gravitational capture to make it go around, orbit around, as a gravitational collision, okay? I'm going to put that collision on in quotes, okay? So what happens? As it captured and then follows this orbital path around the planet and comes out the other way, right? The relative motion of this speed coming in and this u, which is the platform, right? So the relative motion right, gives speed that is equal to vi plus u, right? And of course, this is from a perfect bounce, right? Assuming like no energy is lost, okay? But now, planet acts like, right, because of relative velocity, this thing's coming this way, planet's moving this way, so relative velocity is going to be this plus that, right? Relative speed. So VF, right, which is this. So VF is equal to, right, VI plus U, which is the relative velocity of this relative to the planet, plus U, which is the platform, right? Which is the platform. So this here is planet acts as the moving platform, like the basketball, right? Right? Like the basketball, right? Therefore, my VF is equal to the initial speed of the probe plus 2U. Okay? So this final velocity of the probe is, so you're going to get a huge boost of getting a gravity assist coming in and then slingshot it off. Okay? All right. Now, the last page. I am not going to do this because this is crazy, but if you want to torture yourself, and if you're a masochist and love pain, you may want to solve this out on your own. Okay? So here's the math behind the tennis ball and basketball. Okay? So we already know the conservation of momentum has to happen. Right? So it's pretty much general M1, M2 collision. Right? So M1, which is like, you could consider that as tennis ball, right? And then M2 as basketball, right? So M1 V1 initial plus M2 V2 initial must equal to M1 V1 final plus M2 V2 final. Right? That's pretty much general equation of two masses colliding. The conservation of energy states, no, we're going to assume that this is going to be an elastic collision, no energy is lost, right? The kinetic energy is pretty much conserved, right? And with with a messy algebra to show, one below, right? But it does work out, right? And two is valid by symmetry equation, right? Just switch the subscript 1 and 2, right? We're going to get this mess, okay? And we're going to get this mess. Okay, we will, if you do plenty of algebra. This is how like college like textbook's going to look like. They're going to go from this straight to here, and they're going to say, well, with the simple algebraic manipulation, you'll end up this. It's obvious to see that. And you're going to see that in a lot of like upper level textbooks. All right. But it sometimes takes about 2 pages to go through this. But I'm not going to do that. That's a waste of time. All right. But if you were to make M2 a lot bigger than M1, like a planet and maybe a spaceship, right? Or basketball and tennis ball, right? You'll end up with this. Okay. You'll end up with that. And of course, the V2 final is going to be the same as the initial V2 initial, right? Because it's going to come down and it's going to go back up as the same way. All right. And it does work out to be 3v. Okay. Again, I'm not going to go crazy and make you guys derive all this, but I think it's cool to know that this happens. And the ping pong ball. Many of you may think it was 4, but it's actually 7. Therefore, it becomes 49 times the height of the original height. All right? And that concludes this chapter. Now you should be working on your homework problems. All right? And, yep. Any questions? All right. I will stop my lecture here for today.